Good morning everyone. My name is Pritam Shete. I am pursuing PhD under the guidance of Professor S.V. Patil sir. The topic of my paper presentation is Azoles in Focus, Eco-Friendly Synthesis and Versatile Pharmacological Potentials. In this presentation, I am going to cover introduction, literature review, classification, synthetic methods, applications and conclusion. Let's start with introduction. Azoles are important class of heterocyclic compound which is useful in organic and medicinal chemistry. They are 5-membered rings with aromatic character containing nitrogen atom and often associated with oxygen or sulfur. High electron richness and metal binding ability make them suitable for chemical reactions. Key members are imidazole, pyrazole, oxazole, thiazole, etc. They are found in natural substances, metal ligands, and farm chemicals. They can fight against fungi, bacteria, viruses, inflammation, etc. We can prepare them by joining simple starting materials in cyclization reaction. Now let's discuss literature review. In 2018, Zhang developed multi-azole hybrids which shows SARS-CoV-2 inhibition and strong cytotoxicity. In 2021, Moxie and co-workers synthesized fused azoles, diazoles, and triazoles, which shows antibacterial action. In 2022, Basu tested pyrazole, imidazole, and triazole via docking and ADMET tools and correlated it with antimicrobial and anti-cancer effect. Al-Hazmi in 2023 reviewed hybrid azoles and metal complexes and highlighted strategies to beat fungal drug resistance. Kumar in 2024 created triazole-based azoles which are active against antifungal infections like Candida and Aspergillus. Let's see classification of azoles. Azoles are classified by several ways. First one is based on number of nitrogen atoms and subclasses are mononitrogen azoles like oxazole, thiazole, dinitrogen azoles like imidazole, pyrazole, trinitrogen azole, example 1,2,3-triazole, 1,2,4-triazole, tetranitrogen azole, example tetrazole. Next classification is based on the saturation level where subclasses are azoles which are fully aromatic, azolene which are partially saturated, azolidine which are fully saturated. Next is based on the substitution pattern where azoles are classified as unsubstituted azole, monosubstituted azole, polysubstituted azole and fused ring system azole. Here I am showing examples of some azole compounds like oxazole, thiazole, pyrazole, tetrazole, etc. These are some drug molecules available in market which are containing azole as an integral part of their structure, which itself proves importance of azole in drug discovery and development. This is flowchart containing different synthetic methods for imidazole, pyrazole, tetrazole, etc. Now let's discuss some methods in detail. First one is click chemistry, where azide is treated with terminal alkyne in presence of copper as catalyst, and at the end we are getting 1,4-disubstituted 1,2,3-triazole. Next method is NOR-type pyrazole synthesis, where aryl hydrazine is treated with 1,3-diketone in presence of acid as catalyst to form substituted pyrazole. Let's see isoxazole formation from nitric oxide. Here nitric oxide is treated with alkene or alkyne. 3+2 cycloaddition will occur and isoxazole is formed at the end. Another method is sonochemistry which acts as a green approach to prepare nitrogen and oxygen azole. Here ultrasonic irradiations are used to speed up the reaction. Acetyl acetone is treated with hydroxylamine to form isoxazole. Next is multi-component construction of azole. Here, active methylene compounds such as malonitrile, it is treated with phenylhydrazine and aromatic aldehyde to form pyrazole derivative. Next, micro-assisted triazole and imidazole synthesis. Here I have shown Debus-Radziszewski imidazole synthesis. Four starting materials are there: aldehyde, 1,2-diketone, amine, and ammonia source. Microirradiations are bombarded and imidazole is formed at the end. Hench-thiazole synthesis, where alpha halocarbonyl compound is treated with thioamide or thiourea. After dehydration, thiazole is formed. Another method is synthesis of tetrazole by reaction of azide with cyanide or isocyanide. Here 3+2 cycloaddition will occur and tetrazole is formed as product. Let's see applications of azoles. Azoles can act as antifungal agent, antiviral agent, antibacterial agent, anti-cancer agent, etc. Let's discuss some applications in detail. Azoles like fluconazole, voriconazole are used to treat fungal infections like candidemia, aspergillosis, and cryptococcosis. Some triazoles and imidazoles shows activity against gram-positive and gram-negative bacteria. Benzimidazole derivatives can stop growth of cancer cells. Azole compounds and their hybrids are having antiviral potential as they can block SARS-CoV-2 enzyme. Azoles can selectively inhibit COX-2, reduces pain and inflammation in conditions like arthritis. Certain azole hybrids have activity against Mycobacterium tuberculosis and can target cell wall related enzymes. To conclude this presentation, azoles are important class of heterocyclic compound useful in medicinal chemistry and organic chemistry. We can prepare them via multi-component reactions, click chemistry, cycloaddition, and condensation methods. They are having diverse range of applications in the field of drug discovery, material science, catalysis, and agriculture. They are having diverse biological activities like antifungal, antibacterial, anti-cancer, antiviral activity. Their structural diversity and pharmacophoric nature make them key scaffolds in medicinal chemistry research. These are few references which I used for this presentation. Thank you so much.